Sometimes we're faced by situations that seem complicated, or where too much information is counterproductive. Take this car. Thinking about how it works doesn't make my driving better. I take the information I need and disregard the rest. And something similar is true of mathematical modeling. When a mathematician's faced with a situation to model, they pick out the relevant information and express it mathematically. Although modeling may be used in many different ways, the same types of equations do often appear. These may be differential equations, networks, but frequently they're simultaneous linear equations, which involve only multiples of each unknown. A solution to the system is a set of values that simultaneously satisfies all of the equations. But are they simply abstract ideas? To find out how they're used, I took a walk on Dartmoor. I mean, surely simultaneous equations are just a mathematician's toy. I mean, they don't have any applications in the real world, do they?
But they do, and in the most unexpected ways.
Horse nutrition benefits directly from the use of simultaneous linear equations. As a free-roaming animal, the horse can graze grassland, eating enough to maintain a healthy body weight. But when the animal is set to work, it needs more energy but has less time to graze. Yet the horse still has requirements that need tackling. What's needed is a supplementary food to give the daily calorie intake, provide a balanced diet, and maintain good health. But it's not a straightforward process.
The most important aspects of the horse's diet is digestible fibre. This is because the horse has to produce about 3/4 of the energy to maintain itself from the products of fermentation. It subcontracts, in a way, the duties to bacteria and protozoa in the hind gut, and thus it is not only just dependent upon what it eats, but it's also dependent upon the population and the healthy climate of the bacteria. So we have to feed not just the horse, but we have to feed the bacteria. Bacteria have a short life when not provided with the right digestible fibre, so digestible fibre has to remain number one.
Trying to create a balanced diet for a horse is a complicated process. The horse has to receive the right proportion of each food group to remain healthy. So, each food group needs to be ranked according to its importance to the horse.
In horse nutrition, we tend to try and achieve certain things at certain times. There is no point going to spend a lot of time on number 58 when we haven't got the first 5 right. And so we divide it up very naturally. And we divide it up into really basically 7s, strangely enough. The first 7 are in fact involved with the energetic part of the diet, those products that provide us with energy.
The horse needs the correct amount of each of 7 important food groups, including starch, protein and fibre. It takes a mixture of these types of food to balance the diet, and that relies upon simultaneous equations.
Simultaneous linear equations come into horse nutrition because we are actually, as the word says, simultaneously trying to arrive at a number of answers at the same time.
The nutritionist understands the composition of each of the basic ingredients, such as maize, sugar beet, oats, or barley. What is unknown is how much of each should be added to the final mix. The total energy requirement is then built up with energy from each foodstuff, giving a linear equation. The other dietary requirements, protein, fibre, starch, and so on, also give equations in the system. The 7 basic requirements result in 7 equations. The solution that simultaneously satisfies all of these equations gives the different proportions of each food that need to be added to the mix. But the horse also needs minerals and vitamins to stay healthy.
The introduction of minerals and vitamins into the calculation does make it difficult because they don't normally appear on their own. They are in fact actually perhaps part of a small parcel of feed, maybe a vitamin or a mineral premix, or they might very well be part of a background of the original feed. So we have various sources from which we can get vitamins and minerals. This, of course, complicates the mathematical calculation.
The modelling process doesn't end when the equations have been used to balance the feed. An important aspect of mathematical modelling is that you need feedback to test the model. In horse nutrition, this comes from the trainer and from the horse itself.
We have an old sort of adage that if they are right inside, they look right outside. So their coats shine, their skin, when you give it a little pinch, pings back, so you know they're not dehydrated. In themselves, they're very, very jolly, to put it in human terms, you know, and when they're really, really ready to run, they show you all the signs of having a buck and a kick and generally being naughty schoolboys, really.
Not all horses are the same. The racehorse runs short distances flat out. But the endurance horse may cover up to 100 miles in a day. Yet both horses require about the same total number of calories, although they obtain them from different sources. Racehorses need a high starch diet, based mainly upon grains like oats, barley and maize. Endurance horses need long-term energy stores. Systems of simultaneous equations are set up to model the different requirements of these two types of horse.
The difference in dietary requirements between a long-distance horse and, say, a sprint horse is because of the amount of work they're doing and the speed that they're going and the general heartbeat. Higher the heartbeat, then the more glycogen or more animal starch, more utilization of energy without the presence of oxygen is needed.
The dietary needs of the racehorse and endurance horse are very different. With as many as 60 equations in each model, the job of the horse nutritionist would be virtually impossible without the use of these mathematical tools.
Mathematics is so important to the nutritionist that you might as well not get out of bed in the morning without it. It is involved in every facet of what we do in trying to get horses to run better and to be more healthy and to breed better.
So horse nutritionists use simultaneous equations to balance diets. But what about humans?
Human nutrition can be balanced in the same way using simultaneous equations.
So why not?
Would you like to feel you're being fed by equations?
Well, I suppose not.
There is a group of people who are happy to get mathematical advice on their diet. Athletes.
This is Burton Technical College, home to a new course on sports science.
In order to prepare for a race, every type of athlete needs to take into consideration their diet, because it's from their food that they get their energy supplies. And so the mathematics comes in based on the amount of energy that each type of food group will provide them with. And it's important to work out what sort of diet to give particular athletes preparing for certain types of races.
The sprinter has to accelerate throughout a race, requiring fast-burning energy and explosive power. The distance runner has to maintain speed for a long period of time, and then perhaps give a spurt of energy at the end. Much like the endurance horse, this requires a very different diet from the sprinter.
A marathon runner needs to build up stores of carbohydrate in their muscles. And in order to do that, what they can do is to try and get rid of as much carbohydrate in their muscles as possible about 6 days before the race. So they would start to eat something typically like fish and chips, which contain an awful lot of protein and fat, but not so much of the carbohydrate. And then they would move on to some of the things that you see here, like the cereals, the pasta, the baked potato, and of course the bread, which are heavy in carbohydrate but not so high on fat content. Mixed with that, you would need a good selection of vegetables and the fruit in order to provide the normal balance of minerals and vitamins which anybody needs. What a sprinter would do is to have a typical mixed diet of things like nice healthy chicken balanced against the salad and the fruit, and of course they can drink really any sorts of drinks, but the emphasis is still not on loading too much with glucose.
Both athletes may require the same number of calories to achieve their targets, yet the types of foods that they're using are different. It's the sports nutritionist's role to tackle this problem.
The value or the use of simultaneous equations would be in calculating the amounts and relative proportions of the different types of food groups that they would need in order to supply a certain type of athlete and a certain sized athlete with their requirements for the race. I don't believe that they could do these calculations without using these simultaneous equations which bear in mind the different needs of the different athletes.
So there are plenty of ways in which people use simultaneous equations.
Yes, they come up in a lot of situations, but sometimes in a more roundabout way.
This quiet residential street in Munich is home to the offices of Herr Werner Stengel, civil engineer. Yet the peaceful exterior hides the exciting nature of Herr Stengel's work. Roller coaster design. This is the Nemesis at Alton Towers, one of the most popular rides ever built.
Brilliant. Honestly, I was so frightened, but it was really good. You've got to try it. All over very quickly, that's the only thing.
I'm still shaking.
So, you don't open your eyes and you're okay, aren't you? And you can tell when you're going upside down because you sort of go over that way.
Nemesis is well known for being a particularly thrilling journey, but it's also one of the smoothest roller coasters around.
Wenn wir den Rollercoaster für Alton Tower, der unter dem Namen Nemesis bekannt ist, entworfen haben, das ist ein Inverted Rollercoaster, das heißt, die Menschen sitzen unterhalb der Schiene. Dann haben wir Cubic Spline Funktionen verwendet, weil diese Funktionen in der zweiten Ableitung mindestens noch stetig sind. Und das ist ganz wichtig, dass die Beschleunigungen nicht sprunghaft sich ändern. Denn das ist etwas, was der Fahrgast sehr schlecht verträgt. Und wir wollen ja einem Rollercoaster-Fahrgast sehr viel Freude bereiten und nicht Schleudertraumas oder gebrochene Collarbones.
A roller coaster needs to change direction and speed rapidly to give the passengers the thrills they expect. The smoothness of the ride depends on the continuity of the rate of change of the gradient. There must be continuous curvature. But a roller coaster is simply a collection of points or nodes that need to be joined with a curve. There is a variety of ways of joining those dots. What is needed is a curve that feels smooth to the rider, and that's achieved through cubic spline interpolation.
Eine Cubic Spline Funktion ist eine Exponentialfunktion, mit der man im Raum Kurven entwickeln kann. Bei einer Achterbahn haben wir vorgegebene Punkte und durch diese Punkte legen wir mit einer Cubic Spline Funktion eine Kurve. Und diese Kurve hat den großen Vorteil, dass sie glatt zu fahren ist und in der zweiten und dritten Ableitung noch stetig ist.
It's easy to join these 5 points with straight lines, but this wouldn't give a very smooth ride. Fitting a quadratic curve between each pair of points successively looks smoother as the gradient is continuous. but the exaggerated peaks and troughs could make this an unpleasant and even unsafe experience. Using cubic equations and matching the gradient and its rate of change, we arrive at a smooth but exhilarating ride with the minimum number of equations. To find this cubic spline curve, we need to know the equation that describes the curve between each pair of points. This results in a system of simultaneous equations.
Wir haben Stützpunkte. Durch diese Bahn muss die Schiene der Achterbahn verlaufen. Und bei einer normalen Achterbahn haben wir bis zu 1000 Stützpunkten. Jeder Stützpunkt hat 3 Freiheitsgrade, sodass wir bis zu 3000 lineare Gleichungen haben, die gelöst werden müssen.
For a roller coaster with 1000 points, the cubic spline interpolation gives 4000 unknowns, but it gives 2 equations less. If a system has a solution, then it must have either one unique solution or it has infinitely many. And even with this large number of equations for a roller coaster, we still don't have enough constraints to get just one curve. There will be an infinite family of curves. The designer needs to specify start and end conditions, giving 2 more equations. This will then generate just one unique curve.
Die einzige Möglichkeit bietet der Computer, weil wir hoffnungslos verloren wären, zu versuchen, sowas noch von Hand zu lösen. Und die Werkzeuge im Computer sind heute so, dass man eine Matrix invertieren kann und bekommt bei den schnellen Computern sehr schnell eine Antwort, auch über 3000 und mehr lineare Gleichungen.
It's usual to use computers to solve such vast numbers of equations, and here they are particularly well suited, as computers work with arrays, an arrangement of numbers or symbols in rows and columns. Simultaneous linear equations can be represented as arrays in the form of matrices. Indicated by these brackets, a matrix is a rectangular array of elements. Each of the elements in the matrix represents the coefficient of one of the unknowns in one of the equations. Matrices are useful in that all the information they contain can be manipulated efficiently as a single unit. The use of computers speeds up this process, solving the simultaneous equations quickly and benefiting the roller coaster rider.
Der große Vorteil der kubischen Parabeln oder kubischen Spline-Funktionen ist, dass wir heute Rollercoaster entwerfen können, bauen können, fahren können, die wir vor Jahren hätten nie bauen können. Die kubischen Spline-Funktionen machen uns die Kurven so glatt, dass die Beschleunigungsänderungen verträglich sind für den Fahrgast. Und der Vorteil ist, dass wir, wenn der Fahrgast es will oder der Besitzer einer Achterbahn, mittlerweile bis zu 7-mal über Kopf fahren und die wildesten Knoten, Kurven und das mit einem sehr langen Zug und mit sehr hohen Geschwindigkeiten. Das wäre in der Vergangenheit alles nicht möglich gewesen, wenn diese Entwicklung der Raumkurven nicht stattgefunden hätte.
Well, it seems to me, Bridget, that matrices are very useful.
Yes, and under certain conditions they can be added and multiplied in a similar way to numbers. They carry more information.
So, do they have other uses in mathematical modelling?
Well, there's the Markov matrix.
A Markov matrix is obviously a matrix that contains probabilities which show the transitions from one state to the other. The sum of all the probabilities must add up to 1.
Markov matrices are useful mathematical tools. They can be used in modelling long-term behaviour of a system, such as the weather.
Tomorrow, starting off bright in the east, rain pushing up into Northern Ireland, outbreaks of showery rain getting up from the southwest there, and an increasing risk of showers in eastern districts during the afternoon, possibly becoming heavy and thundery in the south.
It may seem that the weather is governed by chance, and it can certainly be modelled that way. Suppose that today is sunny, and that the probability of tomorrow being sunny is 1/2. Then there's an equal chance that it may be rainy instead. If today is rainy, there may be more chance tomorrow will also be wet, and only a 1 in 4 or 1/4 chance that it'll be dry. These probabilities can be displayed as a 2x2 matrix, which shows all the transitions at once. Now it's easy to see what the weather might be like tomorrow. But the real beauty of Markov matrices becomes evident when they're multiplied in chains.
A Markov chain is simply a series of matrices which contain the transitional probabilities. And so if you want to calculate the probability of the system, the item, and the consideration to be in a particular state, then you use the Markov chain, the series of matrices, to calculate that particular probability.
The main requirement of such a chain is that these values of probabilities are the same no matter how many times that state has been visited. In other words, the process is constant and it is what's known as memoryless.
Markov matrices are shorthand representations of systems of simultaneous equations, and when they're multiplied in chains, they can be used in the long-term prediction of the behavior of a system. Suppose that today is sunny, and it is sunny in 2 days' time. In between, it must either rain or shine. The sequence of weather is either sun, 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 or sun, rain, sun. The probability of the first scenario is 1/2 times 1/2. The second scenario is 1/2 times 1/4. The probability of sunshine after 2 days is the sum of these two probabilities. However, if we multiply the Markov matrix by itself once, we get this result. All of the probabilities for the day after tomorrow. This process can be carried out for any number of days into the future.
Well, that's interesting, but it doesn't seem very practical. I can't see a weather reader forecasting a 0.0375 chance of rain in 10 days' time.
That is a problem. All mathematical models have their limitations.
So Markov chains can't actually be used practically.
Oh, they can. They have an important role to play in the reliability of electrical power systems.
At National Grid, we have the job of transmitting electricity around the country. We need to ensure that we can do this safely, securely and reliably, and we need to ensure that we've invested enough in the system to make sure that any breakdowns, any failures to supply are very rare.
Risk and reliability are important factors in the operation of the national grid. High voltage electricity from the power station has to be delivered to a number of substations where the voltage is stepped down by a transformer to a usable level. Each time one of these transformers fails, less electricity can be supplied.
One thing we need to determine is how many transformers we need at the particular substation. These transformers are large, they weigh several hundred tons. You're talking several £1 million for transformer plus the ancillary equipment such as circuit breakers. And so it's important, first of all, that we don't put in more transformers than we need, but also it's very important that we don't put in too few transformers.
The optimum number of transformers can be decided using a Markov process to predict the reliability of such a system.
Reliability can simply be defined as the probability of a component being in a successful state and working state at a given time under specified conditions. So if you take a system with a number of components, these components will jump to different states, and the combination of those states will make sure that the system is either in a successful state or a failed state.
The actual process is to try to identify exactly the states in which each component can reside, combine these states together to form a system state, think about all the possible system states that can exist and how the various transitions can take place between those systems, and that forms the basic model which is then used within a Markov analysis.
We will calculate the transition rates from the upstate to the downstate, from the working state to the fail state, and we'll put those into a Markov matrix. From that, we will then calculate the probability that we've got 4 transformers in service, 3 in service, 2 in service, 1 in service, and even though the probability is vanishingly small, 0 in service. And we will then evaluate whether or not it is appropriate to install yet another transformer, or indeed if we've got one too many.
The probabilities can be taken from databases, they can be taken from experiments done in companies and labs and so on, or can be used as subjective assessment sometimes when you don't have the data.
The probabilities that describe the reliability of each component enable the national grid to take account of breakdowns and repairs. And Markov techniques are useful tools to model the behavior. But mathematics is not the only factor that should be included. Health and safety is directly linked to the assessment of risk and reliability. But what is meant by risk?
It's a consequence of following an uncertain path that we don't know the future to. Reliability, on the other hand, is about the strength of a system, if you like, about how long a system can operate without failing, and that may be in a small component, or it may be a whole system failure, a catastrophic failure of some sort.
Assessing risk and reliability depends upon modelling the likelihood of a variety of scenarios. A model that relies heavily on equations and ideas, like Markov techniques.
The role mathematics has played in risk and reliability in keeping people safe has been a large one. Over the last 20 or 30 years, and indeed with the rapid advance of technology over the last century, the role of quantitative risk assessment, and that involves, of course, mathematics and modelling the risk, has played a tremendous role, and using such modelling processes as Markov processes, fault tree analysis, event tree analysis, and so on. And indeed, the HSE and the Royal Society recently, in the last 10 years, have noted the importance of quantitative risk assessment in the analysis of risk.
Mathematical modelling hinges on the attempt to create a plausible description of how a process works. But like any model, it is never exact. Some aspects may be grossly simplified, but sufficient for the purpose. Modelling is a cyclical process that compares the behaviour of a model to the real thing. It can then be refined to improve that behaviour. It is, by definition, imperfect. And other factors outside of mathematics may be needed to improve the model.
The limits of the mathematical process should be seen as just one part of risk management. There is a paradigm shift coming in risk management at the moment. For the last 30 years, it has been based on maths, and scientists, engineers, psychologists, sociologists are now beginning to realise that it is only one part. You can't model behaviour, you can't model risk perception.
So solving simultaneous equations isn't just an abstract exercise. They do have practical applications.
Yes, although it's not always obvious. They may be hidden deep in a computer program.
But Bridget, how do you know if a mathematical model is right?
Well, there isn't really any definite right or wrong. It's how you interpret the answers that's important.
And whether you find a balance.